All right, so we're going to take a look at symmetry and functions for a quick little review of how that works, or learning how that works. If we have y equals negative f of x, it represents a reflection over the x-axis because we're multiplying our y value by -1. Y equals f of negative x represents a reflection over the y-axis because we're dividing our x values by -1, which reflects it over the y-axis. Y equals f inverse of x represents a reflection over the line y equals to x. So these are the three types of reflections that could happen when we are dealing with symmetry and functions. A function is called an even function if it is symmetric over the y-axis for all values of x. So what that means is that you're going to get a graph maybe like a parabola like this with a vertex at 0, 0, completely symmetric around the y-axis, or possibly maybe a absolute value graph symmetric around the y-axis, something like this, maybe a horizontal line symmetric around the y-axis. But in all of those cases, in order to be symmetric over the y-axis, the function must look the same originally as it would reflected over the y-axis. What this would mean is that the function, which is f of x, must look the same as it would reflected over the y-axis, which is f of negative x. Or, in other words, your original function and f of negative x have to be exactly the same. They have to equal each other. So that's the algebraic condition for something to be an even function, which means that it is symmetric over the y-axis. If I wanted to double check, let's say f of x was equal to x squared, which was that parabola up here in the first part. If I tried to figure out what f of negative x was, we would go negative x and then square it. Negative times a negative is positive, which is x squared, which turns out to be my original function. So we've got f of negative x is equal to f of x. Okay, I need a little bit of room here, so I'm going to do that. A function is called odd if it is symmetric over the origin. Now, origin is 0, 0. It is where the x and y axis meet. And so to be symmetric across the origin, what has to happen is that if there's a point up here, if you look across 0, 0, there has to be another point down here that would be symmetric to it. So one thing that you could do to find a symmetric graph is any kind of line that passes through the point 0, 0. That would work. There's symmetry there around the origin. You could think of a reciprocal function. A reciprocal function is symmetric, so you can see that any point that you pick here would be symmetric across the origin. So odd functions, origin, they start with an O. That's kind of a nice way to sort of remember it. And what happens is that in order to be symmetric over the origin, odd function, the function's reflection over the x-axis must look the same as the function's reflection over the y-axis. Now let's just see if that's true. So I want you to imagine for a second, and I'm going to maybe just draw this down here. Let's say that I had just that reciprocal function, just like that. Okay, that's my original. This is f of x. Now I'm going to graph negative f of x, which is a reflection over the x-axis. So it means that point moves down here, and we are going to reflect it over the x-axis, and this point right here moves up here, and we're going to reflect it over the x-axis. Okay, now I'm going to take a look at a reflection over the y-axis, which is f of negative x. So the points that I'm going to use that one. So that one reflects over the y-axis to get here, so we're going to get something that looks like that. And then this guy right there is going to move over here, so we're going to get that. So notice that in this case, our reflection over the x-axis looks exactly the same as the reflection over the y-axis. And what this means algebraically is that f of negative x has to equal negative f of x. The two reflections are the same. For example, if I have f of x is equal to 1 over x, and I wanted to try f of negative x, I'm going to get 1 over negative x. Or if you want negative 1 over x, which is negative f of x. And so we've proven that that is equal to that, which proves that it is an odd function and that it has symmetry over the origin. A function is called a self-inverse if it is symmetric over the line y equals to x for all values of x. So a self-inverse, something like this, something that's symmetric over the line y equals x. Remember the line y equals x looks like this. So one good example again of a self-inverse would be that basic reciprocal function. It is symmetric because this point and this point are symmetric to each other. And this point, if you reflect across the line y equals x, you're going to get that value. So that is a self-inverse as we're going through here. In order to be symmetric over the line y equals to x, the function must look the same originally, so that's my f of x, as it would reflected over the line y equals x. Now a reflection over the line y equals x, remember that that is f inverse of x. And so what that means is that your f of x function and your inverse function have to have exactly the same equation when you go through this. The other way of doing this, if I want f of x to be the same as f inverse of x, another way of testing it would be like this. If I said f of x is equal to x, because the only way that f of x is equal to x is this property. If you remember, f of f inverse of something is equal to that something, right? They canceled each other out. So the only way that I can pop the x out of this if these are inverses of each other. So f is equal to its own inverse. Okay, those are the three types of symmetry that you could have. Just be aware that for many functions, most functions in fact, you are going to not really even get any symmetry. So you want to we're testing for symmetry. So it says for each of the following functions, determine what type of symmetry there is, if any. What we want to do is we want to start off with f of negative x, because that will determine whether it's even or odd or neither for that one. So for that, I'm going to do function notation, 2 times negative x squared divided by negative x squared minus 4. When I square a negative, I'm going to get a positive. When I square that negative, I'm going to get a positive minus 4. And so what that tells me is that that is equal to my original function. So if you take a look up here, it is equal to my original function. If f of negative x is equal to f of x, then what we get is an even function. And an even function is symmetric over the y-axis. So the way I always used to remember how we were going to go and figure out symmetry over the y-axis is that if I think about saying even, maybe I can say even like this, right? It kind of has like a ye sound in front and might try to help you to remember that it's the y-axis. I don't know if that's going to work, but we'll see. For the second one, we're going to go f of negative x is equal to 2 times negative x cubed divided by negative x squared minus 4. When I do this one, I'm going to get negative times a negative times a negative, which is a negative 2x cubed on the top, and a positive x squared minus 4 on the bottom. If I take that negative out, we're going to be left with 2x cubed over x squared minus 4. And notice that the stuff on the inside of the brackets is my original equation up here. So we've just shown that f of negative x is equal to negative, this is the negative on the outside, f of x, which tells me that this is an odd function, which means that it's symmetric over the origin. That one was more easy for me to remember because odd and origin start with the same letter. By the way, if something is even, there is no possibility that it is a self-inverse because it is symmetric over the line, over the y-axis. There's no way that I could draw this line right here and it be symmetric as well. You do have to check odd functions to see if they're going to be symmetric or to see if they're going to be a self-inverse as well, because it could be more than one thing. So if we have y equals to x cubed, is that what it was? 2x cubed over x squared minus 4. 2x cubed over x squared minus 4. To find the inverse equation of this, you're going to go x equals to 2y cubed divided by y squared minus 4. And pretty much I can stop there. Remember that we would multiply this. X times y squared minus 4x is equal to 2y cubed, and we would have to figure out what y equals. Well, number one, I can't solve for y. Right? There's no way for me to isolate that y cubed and y squared out. Secondly, it sure isn't going to look like this because it's not going to have an x cubed in it. So that means that my inverse function, whether it is a function or not, is definitely not the same as my original function. You don't have to actually finish it up. You can just sort of say that's never going to happen. Okay, so now with our last one right here is I'm going to check f of negative x. So I'm going to get 5 times negative x minus 2 over 3 times negative x minus 5. So that's negative 5x minus 2 over negative 3x minus 5. That doesn't look like the original, but it's close. Maybe if I factor out a negative 5x plus 2 on top, and negative 3x plus 5 on the bottom, negatives cancel, and we're going to get 5x plus 2 over 3x plus 5. So in this form, it's not the same as my original. In this form, it's also not the same as my original. So this one is not odd or even. It's neither one of those. It doesn't have symmetry over the origin, and it doesn't have symmetry over the y-axis. Let's check, though, for a self-inverse. So I switch my x and the y, so I'm going to get 5y minus 2 over 3y minus 5 over 1. Get that common denominator of 3y minus 5 by multiplying this guy by 3y minus 5 is equal to 5y minus 2. So we're going to get 3xy minus 5x is equal to 5y minus 2. And let's get all of our y's to the left side. So if I factor out my y, I'm going to be left with 3x minus 5. I'm bringing that across and factoring it out. And I'm bringing the 5x to the other side, so I'm going to get positive 5x minus 2. Divide by, remember this is my inverse function right here, divide by 3x minus 5, and I'm going to get 5x minus 2 divided by 3x minus 5, which is the same as my original function. So that is equal to f of x. So what we have shown is that f inverse of x is the same as f of x. What we get here is a self-inverse when the original function is the same as the inverse function, and that means that this graph would be symmetric over the line y equals to x. Okay, so that's pretty much it. I'm just going to do a quick little example. So let's say I had given f of x is even, g of x is odd, and let's say we wanted to find f of negative 2. So f of negative 2, because f is even, would be the same value as f of 2. Okay? If g of x is odd, if I wanted to find g of negative 3, if it's odd, the negative is going to come outside, and it would be the same value as negative g of 3. And that is how, when we're dealing with an even function, even, symmetry over the y-axis, even, f of negative 2 and f of 2 are the same. If it's odd, symmetry over the origin, when you put the negative in, it actually pops out and you get that value there. Okay, that's it for that one. Thanks for watching this, and I will see you next time.